So this is the best rainbow I've ever seen. I was standing on a hill in McAlester, Oklahoma, looking off to the east, and there had been a really bad thunderstorm that had passed us and now was to the east. We're looking at it, and the sky behind me was super bright. You not only could see a huge chunk of the rainbow, but you could see a double rainbow off to the side of it. So I have always been fascinated by this. Why can I see different colors? How can the sun be turned into different colors? And so far we've talked about how waves can carry energy. And one of the obvious ways that waves carry energy is sunlight is the primary source of energy for most things on Earth. So in this week of learning, what I want you guys to try to figure out is how light works, how light carries energy, and what the difference between different kinds of light are. One thing about light I suspect you already know is that what we perceive as white light, which is coming out of this light here, can actually be separated into what's called a spectrum. So here's a rainbow, and we can see the rainbow really starts with a very deep dark red, transitions into orange, then yellow, then green, then kind of a bright blue, a darker blue, which is called indigo, and later violet. So what we think of as white light is actually many different kinds of light mixed together. What physically is the difference between those different colors? So as we enter this unit, in distinguishing between different kinds of light, it's important we remember our wave speed equation. Velocity equals wavelength times frequency. Velocity is measured in meters per second, wavelength in meters, frequency in hertz, or 1/seconds. With this equation, we can relate these three concepts, which are very important for light, because light can act as a wave. So we know that the wave equation, velocity equals wavelength times frequency, applies to all waves. And what we found with visible light is the difference between different colors actually is their wavelength, and therefore also their frequency. The purple end of the rainbow has the shortest wavelengths of about 390 nanometers, which is 3.9 times 10 to the negative 7th meters. These are very short distances between wave peaks. But if you go towards the red end, the wavelengths get longer and longer and longer, and the frequencies get lower and lower and lower. So that's ultimately the physical difference between different colors of light. All light, regardless of wavelength, has the same speed, 3 times 10 to the 8th meters per second. It's a value that gets used in physics a lot. So if we know the wavelength of the light we're looking at, we can calculate a frequency in hertz. Just make sure you're using the proper units. It's meters and not nanometers. So every wavelength of light has its own frequency. Long wavelengths have low frequencies. Shorter wavelengths have higher frequencies. Now, where does light come from? It seems to be from wiggling a charge. If you have a situation where an electron or a proton or something charged moves up and down, it creates waves in space in what are called the electric and magnetic fields. We'll study that later. Now, what's important about this part is just understanding that because this is happening in space itself, in these electric and magnetic fields, light waves do not need a medium to travel in. So unlike sound, unlike mechanical waves, this can travel through empty space, which is something you already knew, because honestly, Earth gets most of its energy from the sun. If that was not possible without a medium, we would be in trouble, because there's not a huge amount of stuff between us and the sun. So it's really good this energy can be carried. These kind of random numbers for the colors of light we can see for their wavelengths and frequencies kind of beg the question, why? What is it that makes these particular wavelengths and frequencies special? And the answer is they're not special. The reason these are the colors that we can see is that these are the colors that certain receptors in our eyes are sensitive to. These colors will come in and cause charges in our eyes to start wiggling, which our brain can then pick up. But the truth is, other wavelengths and frequencies do exist. And they can go from much longer wavelengths than red all the way up to much shorter wavelengths than violet. So light is one part of something big that we call the electromagnetic spectrum. And let's look at some of the other pieces of the electromagnetic spectrum. So I'm using the visible spectrum as our reference. And if we go in one direction, in other words, longer wavelengths, lower frequencies than red light, the ones closest to red light are infrared. When you get a little bit longer wavelengths, lower frequencies, that's called microwave radiation. And longer than that, lower frequency than that, those are radio waves. So there's not a fundamental difference between radio waves and, say, blue. They're both electromagnetic radiation, and the thing that's different about them is their wavelength and frequency. If your favorite color is blue, that's awesome. If your favorite color is 98.7 WNLCFM, that's awesome too. They're both just a specific wavelength of electromagnetic radiation. So what I'd like to do now is take a look at some of these other frequencies and wavelengths of light that we can't see. We're going to start with infrared and make our way to longer and longer wavelengths. Once we do that, we'll double back and we'll start with ultraviolet and make our way to shorter and shorter wavelengths. So let's look at an example at how we use infrared light in our everyday lives. One application of infrared light is for TV remote controls to talk to TVs. You've probably noticed that there's an LED on the front of most of your remotes, but you've probably never seen it light up. You may see a tiny reaction in this film, but not very much. Turns out there is a lot of infrared light coming out of this LED, and the reason you're not seeing it is not because the phone can't see it. The electronics in the phone are actually sensitive to infrared light, unlike our eyes. This is an iPhone 6s Plus, and Apple puts a filter in to block colors of light the human eye can't see. So you may be getting a couple of glimmers, but not very much. But just to show you this infrared light, let's take a look at what it looks like through two other phones. This is a fairly old, cheap Android, the kind you'd get at a gas station for about 30 bucks. This is a nicer, more modern Android, and we'll see how much of that infrared light they let through. We'll start with the older, cheaper one. Okay, so this camera does not have any optics to block infrared light, and you can see that the phone is highly sensitive to it. Now it's looking blue-purple. That's not because infrared light has any color. Infrared light actually doesn't, by definition, since we can't see it, but it's just how the phone's electronics are interpreting it as it sends the signal to the screen. Let's take a look at the slightly more modern Android. So in this case, the light is there, but harder to see than with the one that doesn't block any of the infrared light. So at the end of the day, infrared light is very much present in communicating between a remote and a TV. You can see that this is flashing in a pattern. Pressing different buttons gives a different pattern, and that's how the TV knows what you want it to do. So there's lots of colors of light that are out there that our eyes simply can't see. That doesn't mean they're not there, and it doesn't mean we can't make use of them. Let's take a look at some of these other colors. As you go to longer and longer wavelengths, you enter what's called the microwave region of the spectrum and then the radio wave region of the spectrum. These are both really important for how we communicate wirelessly. Most things that communicate over longer distances require either a microwave signal or a radio wave signal. So what I've got here is a list of common wireless devices, just kind of lined up on my classroom floor. And I've got a laptop and an iPad. Well, they communicate over Wi-Fi. And the networks as of 2016 that were commonly in use were these standards. And that's a frequency of 2.4 gigahertz and a wavelength of about 12.5 centimeters. So using the size of the laptop as a scale, I put in what the wave peaks would look like for a Wi-Fi signal in my classroom. So again, about 12 centimeters apart from each other. Some other common wireless devices we use are FM and AM radio. Those have much longer wavelengths. Notice that AM has a significantly longer wavelength than FM. So here's a little radio. The first FM peak would be here. I guess the next one would be somewhere off here. But the AM one can't be pictured because it would be, nearly 300 meters away. AM wavelengths are very, very long. Different cell phones in different carriers in different countries use very different signals because honestly it's up to each country to allocate which colors of light you're allowed to use for any particular signal. So phones have to be built to work on a very specific standard for the country they're being used in. Or more commonly now, they have to be adaptable. Two commonly used kind of regions of the spectrum in the United States are around 850 megahertz, which is a wavelength of 35 centimeters, and then 1900 megahertz, which is about half that. So these pink and brown lines here, those correspond to the two different regions of the spectrum we use for cell phones in the United States. So they're fairly different from each other, and like I said, they're different in different countries. Walkie-talkies use a variety of frequencies. There's CB ones that use very long wavelengths. There's marine radio. The one I have here is the kind you'd buy at a Walmart for buying walkie-talkies. And they use what's called the General Mobile Radio Service. And that has a wavelength of about 65 centimeters. Again, you got to have the right walkie-talkie for the application you want so that the right set of users actually hear you. A GMRS radio is not going to pick up something on the marine channels or the CB channels. The TV channels are tucked in several places around the electromagnetic spectrum. They all have numbers in the United States, but those numbers don't really correspond to the actual wavelength and frequency the broadcast's on. There's generally two big parts, what's called the VHF, and channel 13 is an example of that. So the waves coming into this TV on channel 13 are about 1.5 meters apart. But the other part of the spectrum, the UHF, has waves that are much closer together. Now there's dividing lines in those two, and it turns out that you actually need a kind of different antenna to receive electromagnetic radiation of such different wavelengths and frequencies. Let's look at a typical TV antenna, and you'll see what I mean. So this is a typical attic mount TV antenna, and what you see here is a curved mirror, and bear with me that this is a mirror. We'll talk about that in a minute. And you've got basically these dipoles for getting the different wavelengths of light. So those really long VHF waves, this is the antenna for them. And then the shorter and shorter UHF waves each have their own antennas for different regions of the UHF, depending on how long or short their wavelengths are. So what's the point of the curved mirror? Let's take a look at something similar for visible light, and I think that will make more sense. So you can think of the radio waves as being like these parallel rays of light, and they come into the mirror, and the curved mirror reflects them and focuses them to a point where we expect the light to be very bright. Let's see what that looks like on the mirror with the TV antenna. So because of the shape of this mirror, it's not going to reflect all waves of different wavelengths to the exact same place, and that's why the different dipoles are in different places. But in general, the waves will come in and be focused onto the appropriate antenna for each wave, and then we'll get a stronger signal. Now, I think it's fair to ask, how on earth is this a mirror? And that's really tied to the question of how do all of these devices receive radio and microwave signals inside? Green light can't go through a wall or a roof. Why can FM? Why can Wi-Fi? Why can a cell phone signal? And the answer is materials interact with electromagnetic radiation of different frequencies differently. Things that we think of as opaque or transparent are only such to certain frequencies. So to radio waves, this curved object here acts as a mirror, and that's fine. We'll see that knowing whether something is opaque or transparent to a frequency is important as we get to very high frequency wavelengths as well. So as we just saw, there are physics reasons to use a specific wavelength and frequency for a specific purpose. But it's important to understand that the reason that devices are divided up to use very specific wavelengths and frequency is often also a legal thing. Basically, the electromagnetic spectrum is very valuable real estate. If all people who wanted to use devices to communicate wirelessly could just pick any wavelength and frequency, or in other words, any color of light they wanted to broadcast on, those devices could start to interfere with each other pretty quickly. So I'll give you a funny example of interference. Around 2005, people's garage door openers started going ballistic. And it turned out that the reason for this was the wavelength and frequency the transmitter in your car uses to talk to the opener. It turned out that that frequency was really close to a US military frequency. And the military hadn't used their frequency in a long time. So no one had really known that they were too close together and could interfere with each other. Sure enough, the military started using it again, and garage doors around the country went ballistic. They started jamming in certain positions. But at the end of the day, it wasn't the military that had to change, because they were the legal users of that frequency. So you can see that who's a legal user is actually a political decision. You've probably been driving in your car listening to an FM station like, say, this one, 91.7 megahertz. And as you get farther and farther away from the city it's from, it starts to fade out. And maybe another station starts to take its place. And there's probably a place where you hear both stations at the same time, and it's really hard to listen to. So to prevent that kind of interference for most people in the city listening to that station, certain radio stations buy the right exclusively to use that frequency. And it's the government's job to assign them a frequency and make sure that nearby stations don't overlap, so you get that kind of interference. So there's a pattern as you go around the country of which frequencies are used in different cities. And that's why TV and radio broadcasts in different places are all on different channels, so that each city can have its own set of channels and not interfere with adjacent cities. One final thing worth knowing about all these frequencies and wavelengths is that who's the authorized user of them is actually an important political decision for any country. And there's a lot of competing interests that want to broadcast on certain channels. You could see that, for example, the TV spectrum, the wavelengths are pretty close to that certain cell phones use. And that means it would be pretty easy to reallocate things that we currently use for TV and use them for cell phones or other wireless devices. So there's a lot of money being spent, and there's a lot of political pressure to make decisions to use parts of the spectrum. And you should know that, and you should know that it could have an impact on your life in terms of what services are available. So it's worth paying attention to who uses different parts of the radio and microwave spectrum. Let's return now to visible light, and we'll start to look at frequencies and wavelengths on the purple end of visible light, things of higher frequency and shorter wavelengths. So we'll start with violet, and we'll work our way to shorter wavelengths and shorter frequencies. The next region of the spectrum with slightly shorter wavelengths is called ultraviolet light. Then comes shorter wavelengths, which are X-ray light, and this overlaps somewhat with another region called gamma ray light. We'll talk more about that later. You've probably heard about all these before, and one thing I think you probably know about them is they're all associated with danger. There's something about these that makes us want to avoid these. They can cause anything from sunburns to cancer. But let's talk about why that is, and we'll look at some common aspects of these types of light. So we're saying that things that have short wavelengths and high frequencies have more ability to cause damage than things that have long wavelengths and low frequencies. But that shouldn't make any sense because, the ability to damage something is usually related to energy. And we've seen that with waves, energy is typically associated with amplitude, not with wavelength or frequency. So there must be something else going on here that ties frequency into energy as well as just amplitude. So just to be clear here, you could broadcast a certain amount of energy per second, or power, with any wavelength in the electromagnetic spectrum. You know there's radio stations that can reach across hundreds of miles. They must be very powerful compared to those little FM transmitters that don't broadcast over a distance much wider than your car. So you can transmit different amounts of energy with any frequency in the electromagnetic spectrum each second. That said, though, nobody ever got a sunburn from a radio wave. So there must be something different about how light with short wavelengths, high frequencies, light beyond the violet here, interacts with materials. That's what we have to look at now. So this inability to explain why materials interacted differently with different kinds of light led Albert Einstein in 1905 to propose a new model for light, that light could be seen as a particle, and that each particle slams into material and delivers a certain amount of energy. Building on earlier work by Max Planck, he said that this equation shows how much energy a particle of light, also called a photon, can deliver. E equals hf. In other words, the higher the frequency of the light, the more energy it carries. H is just a constant, so essentially we're saying that when you increase the frequency, the photon gets more energy. And this gives us a reason why high-frequency light behaves differently than low-frequency light. Particles of violet light deliver more energy when they collide with material than particles of red light do. Particles of ultraviolet or X-ray deliver lots more energy than a particle of, say, radio or microwave. So if we think about every particle of light hitting matter as delivering a certain amount of energy, some particles may deliver enough energy to a molecule to cause chemical reactions. Other particles won't. This starts to give us an understanding of why light behaves differently with different frequencies. So the interesting transition happens between when you have a frequency of light whose photons have a low enough energy that they can't knock electrons out of an atom, to when you get to a frequency of light whose photons have a high enough energy that they can do that, or ionize the atom. This type of radiation is now called ionizing radiation. And the reason it's dangerous is if you ionize an atom, it suddenly becomes chemically reactive. And this could break bonds, it can kill cells, it can cause sunburns, and if you're unlucky enough, it can even start to contribute to cancer. So this is a big, important distinction between photons that have this ability and photons that don't. We call this ionizing radiation for that reason. There's not as clear a dividing line between ionizing and non-ionizing radiation as I have drawn here, because every atom is different. So there is some visible light that will ionize some atoms. There is some ultraviolet light that won't ionize other atoms. So don't think that this is a hard and fast line. But the key thing to understand is generally the higher the frequency, the more energy a photon has, and the more likely that particular radiation is to be ionizing. And that's why we have to be careful with higher frequency photons. That's why we worry about ultraviolet, X-rays, and gamma rays. So I'm sure you've been taught from the time you were a little kid to avoid ultraviolet light. There's obviously a lot that comes from the sun. We cover up if we have to go outside. We wear suntan lotion in places we can't cover up. And generally we know that this causes skin damage and skin cancer. We avoid things like tanning beds for the same reason. But not all ionizing radiation is bad if you use it in controlled circumstances. An example of a positive use of the ionizing properties of ultraviolet can be found in this goggles cabinet. This is set to be tightly sealable so no light can get out. And we know that students wearing goggles that other students have worn is kind of gross and a good way to spread bacteria and germs. So if you put the goggles in a cabinet like this, turn on ultraviolet light for a while, eventually enough chemical reactions will have occurred to kill the bacteria and make the goggles safe for the next student to use. So ionizing radiation, if we're trying to cause the ionizations, can be a positive thing. And that's one good use of ultraviolet light. Of all the types of ionizing radiation I listed, The one you're probably most familiar with are X-rays. We use these all the time in medicine and in security to see what's inside an opaque object. But that probably should give you pause now knowing that this is ionizing radiation. Because in theory, X-rays could ionize an atom, break a bond, even cause cancer. So why do we expose people to ionizing radiation for a purpose like that? The answer is relative risk. There's a risk of being exposed to ionizing radiation, but there's also a risk of getting on an airplane if somebody has a bomb, or walking around with a broken bone, or not knowing you have tuberculosis. So at the end of the day, we have to make a judgment call of what is the worst risk. So this X-ray is of my wonderful cat Scout back when she ate a ribbon. And that can be actually really dangerous to cats and dogs because it can lead to intestinal blockage and rupture, which could be fatal. So when we talk about risk, the risk of not knowing what was going on in her body was worse than taking an X-ray. This was a concerning one. These dark spots in her intestines show air pockets. And she passed the ribbon okay, but they were a little worried when they saw this. So the job of a radiologist is basically to determine when an X-ray is warranted. X-rays typically don't have a huge amount of risk to them, but we don't take X-rays for no reason. We take them for very specific reasons so that other hazardous conditions can be ruled out. X-rays like this one are relatively low doses, but there's an obvious limitation to them. This is essentially just a two-dimensional shadow of all the internal structure of my cat. It's all flattened onto one flat image. So there's not a lot of information about what's going on three-dimensionally inside. If we needed that information, which would be important for treating some diseases, there's another kind of X-ray called a CT scan, which involves much higher doses of radiation, but it gives 3D images of what's going on inside. This can really help with certain problems. That being said, doctors and patients have to be much more careful in considering the risks of it, or how many to do. This is a sample of a radioactive isotope called cobalt-60, and it's a source of gamma radiation. Gamma radiation is another type of electromagnetic radiation with very high frequencies and short wavelengths. It's a lot like X-rays and the two overlap. The distinction really is where do they come from. X-rays are usually generated by electrons moving around in atoms, and gamma rays usually come from the nucleus. But it's another type of ionizing radiation and one that we have to be careful around. This is one of the reasons we're wary of radioactive materials. There's other kinds of ionizing radiation that come out of radioactive materials that are not electromagnetic radiation, but that's a topic for a different lesson. So I'm acutely aware that for half this video I talked about the wave properties of light, like frequency and wavelength, and then I started talking about how different particles of light carry different amounts of energy. So which is it? Is light a wave or a particle? The answer is it's really both. This is one of those strange things that happens when you try to talk about things that are so tiny, atomic size or smaller. The models we use in our everyday world sort of break down. So light's not really either a particle or a wave, but there's some things about it that we can understand best by thinking of it as a wave. There's other things about it we can understand best by thinking of it as a particle. So this uncomfortable duality happens a lot in chemistry and physics, and it's worth getting used to it. Remember, it's all just models, and the value of models are their explanatory power. Both the particle model and the wave model tell us some things about light. So I hope after this grand tour of the electromagnetic spectrum, you understand that the difference between radio waves, all the way through visible light, all the way down to gamma rays, is wavelength and frequency. We can use the wave model to understand that. I hope you also understand that how much energy each particle of light carries is based solely on the frequency, and that explains to us why some colors of light can be more damaging than other colors of light. If you understand those things, you have a good understanding of the electromagnetic spectrum.